Hello, and thank you for your interest in our work, Targeted Variational Autoencoder, which was done in collaboration with Najati Jian Jamgoz and Richard Bowden at the Center for Vision, Speech and Signal Processing at the University of Surrey. Machine learning is frequently used as a tool to undertake the task of prediction and forecasting. However, a consideration for causality and the underlying data generating process is beginning to become more common in machine learning. Judea Pearl explained the importance for such a consideration as follows. He said this causal ingredient should allow computer systems to choreograph a parsimonious and modular representation of their environment, interrogate that representation, distort it through acts of imagination, and finally answer what-if kinds of questions. Such questions cannot be articulated, let alone answered, by systems that operate in a purely statistical mode, as do most machine learning algorithms today. So in other words, if we want to be able to use machine learning in order to answer important scientific questions, then causality represents an essential component. The goal of our work is specifically that of causal inference, that is, specifying a causal estimand of interest and estimating this quantity from the available data. Graph A represents a canonical form for an observational study in which there exists pre-treatment covariates X, which include things like age, gender, medical history, and so on, treatment assignment T, which might represent drug versus placebo group, and corresponding outcome Y. One causal estimand of interest is the average treatment effect given by tau, which is defined here as the expected value over the covariates of the difference between the expected outcomes under the treatment and the placebo. Unfortunately, we don't have access to what is known as full data. Full data would enable us to simply compute the difference across all individuals of their outcome under treatment and their outcome under placebo. Of course, people are only ever given one or the other treatment, so the counterfactual outcome is not known. This is illustrated in this hypothetical data set where each row corresponds to an individual's data point, and we can see that the potential outcome under treatment Y superscript 1 is only available if they receive treatment, and the outcome Y superscript 0 is only available if they receive placebo. Causal inference can therefore be considered to be a missing data problem, where we wish to estimate the counterfactual and unknown outcomes using the available data. Incidentally, in randomized controlled trials, the task is simpler because even though we still only have one of these two potential outcomes for each individual, the differences between the treatment and placebo groups, known as treatment assignment heterogeneity, is minimized, enabling us to directly contrast the two groups. The corresponding graph for an RCT is given in graph B, and you can see that there's no arrow going from the covariates to the treatment assignment. In order to simulate the RCT setting, we need to be able to freely intervene on T in order to examine the outcome under our chosen treatment. This is what is conveyed by the do operator in the expression for tau. In order to estimate the causal estimand from the data, in the absence of RCT data, it is necessary to know whether for the given problem the causal estimand is actually identifiable from the data. If we can derive an expression for the outcome given an intervention on the treatment, then we can estimate the quantity using the data that we have access to. In the example given, a straightforward derivation tells us that P of Y given do T is estimable from the data according to the expectation of P of Y given T and X over X. In other words, conditioning or adjusting for X is sufficient. This identification formula means that we can straightforwardly estimate the target quantity using plug-in estimators. Plug-in estimators, Q hat, fit using the data for the expectation of Y given the treatment and the covariates, and we plug these into the expression for our target quantity. The estimated quantity of interest is therefore the average of the difference between the output of the estimator for when we intervene on the dataset to set treatment to 1 and for when we intervene on the dataset to set treatment to 0. The error on this estimate is known as the EATE, which requires access to tau itself. And this is obviously rarely the case because we don't have access to the counterfactual information needed to directly compute it. In order to evaluate our success at estimating the causal estimand, we therefore either need a subset of RCT data or we need synthetic data which we can use as a reference. Nevertheless, the reliability of the estimated value rests on a number of strong and often untestable assumptions. In particular, we assume that there are no unmeasured confounders. If there are, then X may not be a sufficient adjustment set, and our estimate may be biased. One of the proposed methods for dealing with such unobserved confounding is to attempt to infer these unobserved confounders from the observed covariates, specifically what are known as proxy variables, as part of a latent variable model. There are many methods designed for the purposes of causal inference, and there are far too many to cover in this presentation. However, our method is concerned with continuously optimized neural network methods, especially those parameterizing latent variable models, so therefore we'll cover the works most similar to ours. We'll start off by a consideration for causal effect VAE by Luizos et al. In this method, they seek to infer a set of latent variables Z using approximate variational inference such that these inferred latent variables are able to explain the observations and such that they represent a sufficient adjustment set for identification of the causal effect. The assumption is that there exist proxy variables in X from which a sufficient adjustment set can actually be inferred. In our view, this is an important milestone in the adaptation of deep neural network-based latent variable models for the purposes of causal inference. Another related work is Intact VAE by Wu and Fukumizu, which also uses approximate variational inference and attempts to provide guarantees that the inferred latent variable adjustment set is actually sufficient to achieve its purpose. Their underlying model for the data generating process, shown on the left, illustrates the assumed relationships which exist. It can be seen that within the set of variables X, there may also exist subsets XIV, the instrumental variables, XY, the risk variables, and XC, the observed confounders. There are also the parents and the descendants of the unobserved confounders U. An acknowledgement for this broader structure was made actually explicit in TED-VAE, which is another approximate variational inference method. TED-VAE seeks to disentangle these latent factors in a similar way to that illustrated in the previous graph. Finally, DragonNet does not use variational inference and is not a latent variable model, but it does leverage theory from the field of non-parametric and semi-parametric statistics, which is relatively underappreciated in the machine learning community. They use the theory to derive what we refer to as targeted regularization, which we'll discuss in more detail shortly. Our method, TVAE, or targeted VAE, is based off a similar structure to TED-VAE in that we seek to factorize the latent variables into instrumental variables ZT, which predict the treatment, the confounding factors ZC, which predict the treatment and the outcome, and the risk factors ZY, which predict the outcome. But we also introduce Z0, which is there in order to explain the residual variation in X, which cannot be explained by the other latent factors. We refer to these other factors as miscellaneous factors. Identification follows still straightforwardly from adjusting for ZC. Here we depict a little bit more detail, and the separate inference and generation models are shown on the left and the right respectively. We define the corresponding evidence lower bound according to the expression given here. The first term is the log likelihood of the covariates X given the inferred latent factors. The second term is the log likelihood of the treatment assignment given the latent confounder ZC and the latent instrumental variable ZT. And the third term is a log likelihood term for the outcome given the treatment T, the latent confounder ZC, and the latent risk factor ZY. Note that we actually specify separate log likelihoods for discrete and continuous variables, and that's not actually shown or depicted in this expression. The remaining four terms in the elbow represent the Kullback-Leibler divergences between each of the inferred latent factors and their corresponding priors, which we choose to all be isotropic Gaussians. Now let's talk about targeted regularization. Temporarily suspending the notational convention we were using thus far, consider a functional T of empirical distribution P tilde as being our target quantity of interest. Then we can also imagine T of P tilde as actually lying on a path in the direction of T of the true distribution P. In other words, if we have enough data, have an infinite amount of data, we will eventually converge to that true distribution. If we know the directional derivative of T at P tilde, we can actually use this derivative to update our original estimate in a similar way that you might do with a Taylor expansion. And indeed, the process underlying the updated estimator is actually known as the von Mises expansion, which generalizes the Taylor expansion to functionals. This directional derivative can be expressed as the integral of the influence function, or influence curve, given in the second expression here. The target quantity tau can be substituted for the t that we had on the previous slide, and the influence function can be analytically derived as given here. It's usually referred to as the influence curve in the targeted learning literature, so I'm going to use IC from now on. So IC is the influence curve, and this influence curve is equal to 0 when the expression for it has been solved. In order to understand how to solve the expression, we should understand the terms given. Starting with the last term, this is simply the error on the estimation of the average treatment effect, which is 0 at the optimal solution. This term is the residual prediction error of the network, and finally, the term here is the key to the influence curve solution, and this is known as the clever covariate. By creating a linear submodel, we can update our estimator Q0 with some additional amount of h, the clever covariate, which is given in the brackets here. And once the estimator is updated, the epsilon hat term, which was estimated as a coefficient in a maximum likelihood solution to the linear regression, will then be 0, having done this update process. Similarly to DragonNet, we adapt this update process to establish a regularizer which also solves the influence curve expression continuously during the training of a neural network, such that at the optimal solution, epsilon will equal 0. Thus, the final loss is given here as the weighted sum of the elbow and this regularization term. Some more details of the network structure is given here. Each block is a neural network with multi-layer perceptron layers and some nonlinear activations. Note that as with DragonNet and TARNet, we split the prediction of Y into two parallel blocks, one for the case when treatment is 1 and one for the case for treatment is 0. Note that unlike DragonNet, targeted regularization is only applied to the Y block. Indeed, targeted regularization is designed to optimize the estimator of the conditional expectation of the outcome, and it therefore doesn't make sense to apply it to the other parts of the network. Now let's review TVAE's performance. First, we designed a synthetic dataset in such a way that we could assess the contribution of the various aspects of TVAE in an ablation study. The results show that the addition of Z0, which is the miscellaneous factor, as well as the targeted regularization, yields a relatively monotonic performance increase. Similarly, we were competitive and also exceed state-of-the-art on the IHDP dataset. And once again, we see similar performance on the jobs dataset. There are a number of limitations to the method which are important to bear in mind, particularly given that causal methods are not easy to evaluate because they do not fall into the category of typical supervised learning. Firstly, do VAEs actually do what they are supposed to, and do they learn an adequate posterior distribution which is sufficient for adjustment? I recommend these two references for a discussion and exploration of why this may not be the case. In the Locatello case, the reference discusses whether or not we can achieve disentanglement without supervision. But this isn't really applicable to our method because we use supervision from the treatment and supervision from the outcome in order to encourage the disentanglement of these factors. But this does not necessarily guarantee that the resulting latent factors are actually sufficient for adjustment. And the other reference discusses this in more detail, and it is actually the focus of intact VAE. Secondly, we have not directly explored the extent to which TVAE infers latent confounders from proxy variables. So we can't necessarily say how much we can ignore the potential for unobserved confounders to be biasing our estimate. We've only loosely assumed that it would be beneficial to have the capacity to do so in principle. So further work is needed to understand the sensitivity. Thirdly, whilst jobs in IHDP represent staple benchmark datasets for causal inference, further evaluation is needed to assess the efficacy of TVAE across a broader range of datasets. Finally, further work should explore the extent to which targeted regularization is actually doing what it is supposed to, or whether the additional regularization is simply reducing bias indirectly as a byproduct of a potentially degenerate solution to the update process. So that concludes my talk. Many thanks again for taking an interest in the work, and feel free to get in touch if you have any questions.